So, we had finished Gelfand theory and we are trying to use Gelfand theory to prove the spectral theorem. So, we had started with defining certain measures. So, recall that if you have a commutative C star subalgebra of bounded operators on a Hilbert space, the Gelfand transform identifies this commutative C star subalgebra of B of h with continuous functions on sigma, where sigma is the spectrum of this algebra, right. So, that is called, that is essentially what is known as the continuous linear continuous functional calculus, in the sense that if I take a continuous function on sigma, I have an operator. Now, our aim is to extend this to bounded functions on sigma, sigma is the spectrum. Okay. So, that is called the L infinity functional calculus. So, for that we had defined certain measures and we will continue from there. Okay. So, let us quickly recall that and then we will continue. Okay. So, let A be a C star subalgebra, C star subalgebra with the identity operator. Okay. So, now we are looking at algebras which are elements are operators and we have the identity operator as well there. So, it is a C star subalgebra also commutative. Okay. So, we are always looking at commutative ones. Okay. Now, the Gelfand transform identifies A with C of sigma, where sigma was the spectrum of A, right. So, this was a change of notation we employed, spectrum of A. Okay. And using this, so if I take a function here in C of sigma, I have an operator which is T sub f, right. And if I have an operator T here, then the Gelfand transform is a continuous function T hat, right. So, that is the identification, right. So, in other words, if I take T f and look at the Gelfand transform, I should get back my f, right. So, that is the Gelfand transform. Now, we defined measures using this. So, how did we do that? So, I take u and v in the Hilbert space, right, and we looked at f going to T sub f u inner product with v, and this was a continuous linear functional. So, we had mu u v complex regular measure such that T f u v, the inner product, is given by integral over sigma f d mu u v, right. And u v going to mu u v was cislinear, right, cislinear measure valued inner product, if you like. And so, it is linear in u, antilinear in v and things like that, right. And we also had that mu u v equal to mu, well, cislinear means this, it behaves like an inner product, right. Essentially, whatever equalities you have for inner product, we have for. Also, if f is positive, then, well, we saw that if using f positive and so on, mu u is a positive measure, right. And also the norm of this measures v is less than or equal to norm u into norm v and so on, right. In the case of mu u, it will be exactly equal to norm u square, but that is something we will see later on. Okay. So, currently our aim would be to extend the functional calculus to L infinity functions. Okay. So, okay. So, we also, so you can keep in mind the example which we had written down, because I will we'll look at it again and again, so that it is clear what is going on. So, this is my A and h is L2 of 0 1. Of course, A is supposed to be a class of operators. So, the way we identify C01 as operators is multiplication by functions in C01, right. So, if I take f in C01, I can look at T sub f, which is from L2 of 01 to L2 of 01, which is multiplication, right. So, T f phi equal to f times phi, right. So, that is an identification, and that is so the collection of T sub f will be your A, right. So, you can think of this as identify it with T sub f in Z01, and these are going to be bounded operators, right. So, this sits inside bounded operators on H, right, where H is L2 of 01. Okay. And Gelfand transform is identity here, right. So, we have seen all that, and if you look at the way we define these measures. So, this is nothing but integral over 01 f u v bar dx, right. So, this is my measure mu u v, and you can see that it is linear in u, antilinear in v, and things like that. If I change u and v, then I get a complex conjugate, and when it is u, then it is mod u square dx, which is a positive measure, right. So, these things are straightforward. Now, our aim is to extend everything to bounded functions. From continuous functions we go to bounded functions. Okay. So, we are back to A being a commutative subalgebra of B of H with identity, and sigma the spectrum of A. Let B sigma. So, I am not using script B there, it just usual B. So, B sigma is a collection of all bounded functions on bounded let us say Borel measurable. Okay. So, measurable complex valued function, complex valued functions on sigma. Okay. So, all bounded complex valued measurable functions on sigma. Then just like C of sigma, B sigma is also a C star algebra. So, then B sigma is also a C star algebra with the usual is a C star algebra with identity, C star algebra with identity, commutative because the pointwise product, right. So, with the L infinity norm, right, this is the supremum norm, these are bounded measurable functions. So, supremum norm makes sense. So, it is like the L infinity space, right. The multiplication is usual pointwise multiplication, star operation is the complex conjugation, right. So, all these things are true for continuous functions, and the same extends to all bounded functions on this sigma. Okay. Now, consider these measures, okay, define. So, yeah, maybe an exercise before that exercise. Let Q from H cross H. So, H is your Hilbert space, Q is a map from H cross H to C, which is a sesquilinear form, okay, such that modulus of Q u v is less than or equal to some constant times norm u norm v. Okay. So, it is like a bilinear form, except that on the second variable it is antilinear. So, when I put an alpha bar comes out, right. So, it is linear in u, antilinear in v, and it has this property that modulus is less than 2. So, that is like a continuity property, right. So, if you have a sesquilinear form which is continuous, then prove that. So, this is easy. So, prove that there exists an operator. So, there exists a bounded operator T from H to H such that Q u v is actually equal to T u inner product with v. So, if you look at any bounded operator T and form this, okay, T u v, then of course, it is linear in U, antilinear in V. So, it is a sesquilinear form and it is bounded, right, modulus of that is less than or equal to norm T times norm U times norm V. We are proving the converse. So, whenever you have a sesquilinear form of this kind with this bound, then there is a bounded operator T such that Q U V equal to T U T V with, of course, because once it is T U inner product with V, the norm T will have to be less than or equal to C, right, whatever constant is coming here. Okay. So, that is easy. So, that is the way to define certain operators. So, it is enough to define this sesquilinear form which is continuous. Okay. So, that is what we will do. Okay. So, now consider B of sigma. So, remember B of sigma is bound, when I put script B, then that is the Borel sigma algebra. This is B sigma which is bounded functions. Okay. So, I will keep repeating it so that there is no confusion. So, take f in B sigma. So, what I want to do is, if f is a continuous function, the continuous functional calculus, which is essentially the Gelfand transform and its inverse, tells me that if f is continuous, there is an operator T sub f in script A, right. I want to do the same thing for bounded functions. Okay. So, how do we do that? So, define for f in B sigma, define. So, we are going to define a sesquilinear form and see if it is continuous. That will automatically give us an operator by the previous exercise. Okay. So, define Q U V to be equal to integral over sigma f d mu u v. Okay. So, using the continuous functional calculus, we produce these measures mu u v, where u and v are vectors in the Hilbert space. Okay. And they gave us this measure mu, which is a complex finite Borel measure, and now I can integrate it against any bounded function, right, the integral exists, and we see that modulus of Q u v, well, this is less than or equal to, when I take the modulus, I can take the L infinity norm of f outside, and what remains is the norm of mu, right. So, norm of mu v, but norm of mu u v, we know that is less than or equal to norm u times norm v, right. So, L infinity norm of f, norm u, norm v. Okay. So, now we are in the previous situation, previous meaning in the situation of the exercise. I have this sesquilinear form Q and it is bounded, right. It is bounded by some constant times norm u, norm v. So, there has to be an operator, bounded operator, which defines that sesquilinear form, right. So, hence there exists an operator, but the operator will depend on f, right, because I started with an bounded f and I looked at some integral with respect to f, right. So, that I will denote by T sub f, right, in B of h, right. I do not know where it is. So, it is a bounded operator on the Hilbert space H such that norm of T f is less than or equal to L infinity norm of f, right, because that is the constant coming here, and this Q. So, Q u v, that is my sesquilinear, bounded sesquilinear form, that will have to be equal to, given by an inner product, right, T u. Okay. So, remember this is an integral. So, this is equal to integral over sigma f d mu u v. Okay. So, keep this in mind that we constructed the measure mu u v using continuous functions, right. Now, we are using these measures to extend that continuous functional calculus to L infinity functional calculus. Of course, we have to prove various things, but we have at least got an operator for all bounded functions, right. So, let me record that from C sigma we got these measures mu u v, and from here we went to now bounded operators, bounded functions on sigma, right, and use this to get a bounded operator on the Hilbert space, right. So, we had this C sigma to A which was sitting inside B of h, right, that was f going to T sub f. Now, we have bounded functions on sigma to B of h. We do not know where it is landing, it need not land in A unless it is a continuous function, and let us say f going to T sub f, right. All the T sub f's are defined using this integral. So, the identity you should keep in mind always is this integral over sigma f d mu u v, right. When f was just continuous, that gave us a measure, and from the measure we were able to extend it to all bounded functions. Okay. All right. Okay. So, this because the definition is like this is consistent with the definition on. So, notice that this is consistent with the already existing definition, okay, definition on C sigma. In other words, if I take f continuous, then it will coincide with T sub f whatever we had defined earlier using the Gelfand transform, okay, because the right hand side is f d mu v, which is what gave us T sub f in the right. So, okay. So, we have extended this definition of operators from C sigma to bounded operators on bounded functions on sigma. Okay. So, now I can write down the theorem. So, this is called the L infinity functional calculus. So, the Gelfand transform and its inverse is the continuous functional calculus. Continuous functions were viewed as operators on Hilbert spaces, and that identification was everything, right. It was a star isometric isomorphism, and we are going to do essentially the same for L infinity functions now, or bounded function. Okay. So, the map f going to T sub f, okay, from. So, now we have gone to a bigger space, that is B sigma, which is the bounded functions, right. So, bounded functions, okay, on sigma. So, from B sigma into script B h, that is all bounded operators on the Hilbert space. H is a star homomorphism, okay. We can say more things. So, when I say it is a star homomorphism, it respects the star operation. What is the star operations here? On bounded functions, the star operation is the complex conjugation, just like continuous functions on sigma. On B of h, the star operation is the identity, right. So, f bar will have to go to the adjoint of T sub f, that is T sub f star. Homomorphism means f times g will have to go to T of T f times T g, right. So, that is what you mean by algebra homomorphism. Linear etc. is trivial, right. So, because the way it is defined, if you look at the integrals, if I change f to f plus g here, then of course, the integral will split. So, correspondingly T f plus g will become T f plus T g. So, the linear part is generally easy to see, right. It is the algebra homomorphism part which is difficult to prove. Okay. So, it is a star homomorphism, that is the first assertion, and we have additional assertions if S in B of h. So, if S is a bounded operator on the Hilbert space H commutes with. So, remember that the bounded functions on sigma, that is a commutative C star algebra with identity, right. So, its image that f going to T sub f's, where f belongs to bounded functions on sigma, that is also going to be commutative. Okay. So, the image is the commutative subalgebra with identity sitting inside B of h. Now, if I take any arbitrary operator which commutes with every t in A, right. So, A is a smaller algebra here, right. So, A is a commutative subalgebra of B of h with identity, but that is the image of continuous functions, right. So, image of bounded functions will be a much bigger algebra than A. Okay. So, if it commutes with every t in A, then S commutes with every t sub f, f in B of sigma. right. So, the point to note is that the A is sitting inside all these T sub f's, where f is a bounded function, right. A is the collection of all image of continuous functions, right. So, I am saying if some bounded operator commutes with the smaller algebra A, it will commute with the bigger algebra T sub f, where f belongs to bounded function. B, if Fn converges to, so Fn's are bounded functions, okay, and Fn converges to f, well, we will call it P dot B, that means pointwise and boundedly. What does that mean? That is Fn x converges to Fx for every x in sigma. So, pointwise convergence, and boundedly, boundedly means all the Fn's are bounded by a fixed constant. Okay. So, mod Fn is less than or equal to k. So, maybe supremum over n. So, in particular f is also bounded, right. Fn's are all bounded by a fixed k, and so Fn's are also bounded, right. So, when I write Fn converges to f pointwise and boundedly. So, pointwise meaning at each point, boundedly would mean something like this, right. So, f is also bounded by k, the limit is going to be a bounded function in B sigma. Then T sub Fn, so these are operators which we defined, right, will converge to T sub f in the weak operator topology. Okay. Well, what does weak operator topology mean? Tfn acting on u inner product with V will converge to Tf acting on u inner product with V, right. That is the weak operator. Will this is a weak result, we will strengthen it later. We will see that something more is true as we go along, but right now this is what we can prove. Okay. Okay, so proof. So, the main part is that f going to T sub f is a star homomorphism. Okay. We know that it is bounded, right. So, because Tf is bounded by, the norm of Tf is bounded by L infinity norm of f, that we know. Okay. So, some parts are easy. So, clearly the linear part is easy. So, f going to T sub f is linear from bounded functions on sigma into bounded operators on H, right. So, that is a easy part. Now, I want to say it respects the star operation. So, now if f belongs to B sigma, okay, we look at Tf u, well, I want to look at f bar. So, the star operation in B sigma, that is bounded functions, would be just taking the complex conjugate, right. So, look at, okay, let me write consider T f bar, right. So, f bar is the star operation in B sigma. I want to say that it goes to the star operation on the other side, that means T f bar should be the adjoint of T f, right. So, T f star. Okay, so, I compute this, okay, using the definition. This is equal to integral over sigma f bar d mu, the measure, right, mu u v. Okay. Remember, mu u v has ciscilinear properties, right. So, I can write this as, so I take the bar outside. So, I have the complex conjugate of f there, that complex conjugate I take outside. So, I will have sigma f, but what is the complex conjugate of mu? Well, the order of u and v will change, right. So, I have v comma u, and then you take the complex conjugate outside, which is equal to, so I have the complex conjugate. If you look at the integral, that is integral of f d mu to vectors, and that we know is T sub f inner product with the vectors, right. So, this is simply T sub f acting on the first vector, which is v now, because we have changed the order, inner product with u, right. So, that is how it is, which is equal to, because now it is the standard inner product. So, if I put a bar, the order changes. So, that is just u T sub f v. Okay. So, T sub f I take to the left hand side. So, that is the adjoint of T sub f u v. Okay. So, now if you look at this, we started from T f bar acting on u inner product with v, we got T f star acting on u inner product with v, right. So, this implies T f bar is equal to T f star, right. So, the map we have just defined f going to T sub f from bounded functions on sigma to bounded operators on H respects the star operation on both sides, right. It is linear, we know, it is star, it respects star operation, we know, and it is multiplicative, it is a multiplicative homomorphism or an algebra homomorphism restricted to the continuous functions, that we already know, right, that was part of Gelfand theory. We want to extend it to all bounded functions. So, here that for that we do the bootstrapping method. You start with f and g continuous and then go take one to bounded function and take the other one to bounded function, and we are done. Okay. So, next to see that T f g equal to T f times T g, right, for f and g in B sigma. Okay. So, now onwards you have to keep track of where are these functions. Okay. So, recall that this is true, for f and g in C sigma, right, that is the continuous functions. Okay. From that continuous functions we want to go to all bounded functions. Okay. So, use the continuity continuous functions first. So, you take f and g in C sigma. So, I will have integral f g d mu u v, right, sigma, this is equal to, well, it is T sub f g, but f and g are coming from continuous functions. So, it is simply T f T g, right, as long as f and g are continuous. Okay. So, that much is Gelfand theory. This is equal to, now think of T g u as a vector. So, that inner product is T f acting on some vector inner product with v, that would be integral of f with respect to an appropriate measure, right, that is how these things are defined. So, this is integral over sigma f d mu, well, the first vector now is T g u and second vector is v, right. So, that is how it would look like, but this is true for every f in C sigma, right, and g in, so g for the time being fix g in C sigma. Okay. But think of now this as a, so this is a measure. Okay. So, g times d mu v is a measure, I have f here and I have f here and I have another measure here, and this is true for every f C sigma, right. So, because of uniqueness and so on, so this immediately implies, right, both are complex regular Borel measures. So, they will have to be equal. So, g d mu u v will have to be equal to d mu T g u v, okay, for every g in C sigma, okay, and u and v in the Hilbert space. So, we have this particular identity which is not very difficult to see for continuous functions. Okay. Now, remember we started with f and g in continuous C sigma continuous functions. Now, let us push one to bounded functions. Okay. So, because I have two measures to be equal, if I integrate against a bounded function they will be equal still again, right, because these two measures are equal. So, if f is a bounded function, then, so now f is a bounded function not a continuous function, then because these two measures are same, integral over sigma f times the left hand measure, that is g d mu u v, will have to be equal to integral over sigma f d mu, well, on the right hand side it is T g u comma v, right, these two will have to be equal. Okay. Well, where are the functions? F now is a bounded function, not a continuous function, but G is still a continuous function. Okay, we have not pushed G to bounded function, there G is still continuous. So, this is true for every F in B sigma bounded functions, right. This is equal to, so if I look at the right hand side, well, this is integral of f with some measure, right, mu some vector another vector. So, by definition this is simply T f acting on the first vector, which is T g u, inner product with the second vector, right, this is how it is, okay, which is equal to T f T g u v. Okay. So, we continue, well, this is equal to, so as I said this will be bootstrapping. So, now we will be able to take G to be a bounded function instead of a continuous function. Right now f is bounded, G is bounded, G is a continuous function. I want to sort of further go to bounded functions, so in the G direction as well. So, this is nothing but T G u comma T f star v, right. So, more or less straightforward, which is equal to, so let us keep that in the screen. So, this is equal to integral over G d mu u T f star v, right. So, that is the, so think of this as a second vector, then T g acting on u inner product with second vector is integral over G d mu with the first vector and the second vector, right. So, we started with this, right. So, let me write down that once again. So, this is equal to f g d mu u v, okay. This is true for every G continuous, right, and every F bounded. Okay. So, I have the G here and I have the G here. So, this measure and this measure will have to be same, right. So, let us right whatever is other than G, right, those two measures will have to be same. So, let us write down that implies d mu u T f star v equal to f times d mu u v for every f in B sigma, right. Earlier we had this only for continuous functions, now we have it for all bounded functions. Okay. Because these two measures are same, now we can integrate against any bounded function. Hence, for any G bounded, right. So, earlier G was a continuous function, now I have gone to bounded function. I have integral over sigma G d mu T f star v equal to integral over sigma G, well, the measure is f d mu u v, right. So, this and this were used. Okay. So, now we are almost done. T f T g u v, if I look at this, I want to say this is T f g, right. So, this is equal to T g u T f star v, we just take the T f to the other side, which is by definition integral over G sigma d mu u T f star v, right, the second vector, but use this. So, this is equal to integral over sigma G f d mu u v, right, which by definition is T f g acting on u v, right. So, think of this as one function and then you have that, right. So, I started with T f T g acting on u inner product with E, I ended up T f g acting on u inner product with E. Okay. So, T f T g equal to T f T g for every f and g in bounded functions, right. Now, I had changed f to bounded functions and g also to bounded function, right. So, that proves it. Okay. All right. So, this, so maybe we will stop here. This proves that the map f going to T sub f respects the star operation and it is a algebra homomorphism, right. So, it is a star algebra homomorphism which is continuous, and there are two more assertions we will prove that in the next lecture. Okay. So, we will stop here.